Good morning or good evening, especially for those of us who are not in Australia. In my case, I'm very glad to be the host of this panel of the Global Innovation Summit on innovation breakthroughs for the economies of the future, with a special emphasis on health. And when we discuss breakthroughs in health within the current global context of lockdowns and before the systemic impact of COVID-19 on the economy, it is noteworthy to emphasize the role played by public or privately funded national research institutions and universities. And if I may speak on behalf of so many of my colleagues worldwide, it is fair to say that universities, as well as research centers and great national research institutions, have been at the forefront of the developments in recent times, from genome sequencing to the development of vaccines, with the implementation of technologies such as with the use of high-performing computing. And it is these breakthroughs that have clearly accelerated the development of solutions to fight COVID-19. At my own institution, where a new medical school has just recently been created, our School of Biotech has partnered with the American firm Amaris and the Infectious Disease Research Institute in the US to advance a new RNA vaccine platform. And the collaboration will combine IDRI's vaccine platform with Amaris semi-synthetic squalene, developed by a joint team with the university, offering differentiated advantages over other RNA vaccines, including superior scalability, efficacy, and sustainability. The pandemic has shown that health is not simply a given of societal well-being. It is where the war over national security and the projection of power is being waged, and we heard that as well from the Australian minister just recently. It is of particular importance to articulate national policies with scientific developments that will not simply create value for the economy and ensure security, but also support societal development and allow individuals to live safer, healthier, and happier lives. For this aim to be accomplished, emphasis on solid and cutting-edge research infrastructures and a robust R&D system integrating industry and universities, as well as support for innovative training in medicine and in the health sciences in general, is absolutely of the essence. And this is clearly what our two speakers now will be talking about. I'm proud to host Professor Dr. Thomas Zachariah, Director of the Oak Ridge National Laboratory, and Professor William Rawlinson from the University of New South Wales, to thought leaders at the forefront of the technological revolution in health. And without further ado, I give the floor to Dr. Zachariah for his initial intro.
Thank you, Isabel. Once again, let me also wish you warm good evening or good morning, wherever we all are. Just to give you a brief introduction to the institution that I lead, Oak Ridge National Laboratory is the largest of Department of Energy's science and energy laboratories. The department's mission is to ensure America's security and prosperity by addressing its energy, environmental, and nuclear challenges through transformative science and technology solutions. Those solutions are delivered by DOE's 17 national laboratories. It's a system of 17 labs. These institutions constitute a national network for research and development. We employ thousands of scientists and engineers who typically work together to solve large-scale, long-term problems using distinctive scientific facilities. So that's sort of a distinctive feature of these national labs as opposed to academic institutions. When the threats posed by COVID-19 began to emerge, the department at its national laboratories moved quickly to find ways in which to put the resources of these institutions to work. Oak Ridge, for instance, is home to the US Department of Energy's most powerful open computing system. So it was no surprise that some of our first COVID-related work involved the use of these systems and the associated expertise. Earlier in the process, the COVID-19 High Performance Computing Consortium was stood up, bringing together computational resources at 6 DOE national labs, as well as those at universities and industry. This consortium of over 30 institutions made these leading computing resources available to the broad R&D community to fight the COVID emergency. Summit, the supercomputer at Oak Ridge, was part of this consortium. We have made the Summit system available to researchers from other institutions for COVID-19 research. These institutions include such institutions such as Cleveland Clinic, IBM, several universities, and other national laboratories. Our researchers use Summit to test billions of candidate small molecules as potential antiviral drugs, something that would have taken months with conventional computers. But because Summit uses 27,000 sort of NVIDIA GPU voltas, it was able to screen 1 billion candidates in a single day. Several dozen early hits were identified, and with university and pharmaceutical collaborators, these hits are being assessed in laboratory tests as promising antiviral candidates. The Summit system was also used to compare the genes of 9 COVID-19 patients to those of 40 uninfected individuals to see which genes were normally co-expressed or turned on or off at the same time. So what the Summit allows us to do is to run these 2.5 billion correlation calculations to elucidate the normal regulatory circuits and relationships for the genes of interest. The results suggest that a cascade of events in the bradykinin system may be responsible for the wide variety of symptoms seen in COVID-19 patients. ORNL researchers, in concert with colleagues at other national labs, are employing artificial intelligence techniques to build an integrated resource for pandemic monitoring, modeling, and analysis. This platform has been used to forecast disease transmission, stress on public health infrastructure, and economic outlook for the nation. The results have been used to support decision makers in DOE, the National Security Administration, National Nuclear Security Administration, and the Federal Emergency Management Administration, or FEMA, as well as officials in states and cities across the nation in answering questions such as what is happening in different regions of the country, how are different areas and populations responding and reacting to conditions and interventions, and how has personal mobility impacted disease spread. This becomes particularly important as we go into the holiday season. Our researchers are also using data mining to advance our understanding of COVID-19 diagnosis, treatment, epidemiological, and management challenges. Modeling is providing deep insight into how the virus is transported in such spaces as open rooms, offices, bars and restaurants, schools, as well as transportation hubs. ORNL is also part of a consortium called Accelerating Therapeutics for Opportunities in Medicine, or ADAM. This is a public-private partnership which is focused on using machine learning and AI to dramatically reduce the time it takes to discover and develop new medicines. ADAM applies computational workflows and supercomputing to optimize the safety and effectiveness of new molecules with the potential to become drugs. The computational tools being used by our partners are currently being used to accelerate cancer drug discovery as well. Working together, the partners are now applying these tools to analyze a growing volume of data on the interactions of small molecules with SARS-CoV-2 proteins. In another example of applying an existing tool to a new problem, we have made our LandScan database freely available to the public for COVID-19 response efforts. This is a global population database, and you can see developing and operating distinctive scientific facilities like our supercomputing and making them available. As you might expect, our response extends beyond our computing facilities. We are using our neutron sources that we operate for the Department of Energy to examine the structure, dynamics, and function of viral proteins and their complexes with RNA and membranes. We worked with industry to develop and deploy new designs and materials for personal protective equipment, such as masks and face shields, and new techniques for accelerating the manufacturing of these vital supplies. We continue to seek out opportunities to put our resources and expertise to work on this challenging global problem. We're open to new partnerships that will help all of us in crossing the chasm the pandemic has created. So I look forward to listening to the next speaker and engaging you, and would be happy to answer any questions. Thank you.
Thank you very much, Dr. Zachariah, and I pass on to.
So thank you very much. It's great to be here, and the invitation is very welcome. I'd also like to thank the Australian Department of Health for their support, and what I'm going to talk about is funded through the Medical Research Future Fund, and I think it's great foresight to look at whole genome sequencing. My background's as a medical virologist. My PhD is in molecular biology from the LMB in Cambridge, and so my interest in this is really how do we identify SARS-CoV-2 variability, and how do we see the changes that are occurring in real time. The grant that I'm going to talk about, I've listed the specific aims here in the team, and I won't go through them in detail, but essentially what this is a way of building systems. It's a way of building expertise, and it's a way of building infrastructure for this pandemic, and in some ways, sadly, for the next, because our planning is really around not whether, it's when. And so in many ways, our responses for this pandemic have been built over the last 20 years. The international reach of this project is through our collaborators and through the databases such as GIS and the use of national databases such as AUStracker. The importance of national genomics cannot be understated. The whole genome sequencing that we do is really somewhere between a routine and a research piece of work. And so the protocols that we use are looking at sequencing from multiple sites. So there are translational and pragmatic issues with that you can imagine, because we typically have state-based implementation of whole genome sequencing. But of course, in terms of utility, what we're thinking of is national utility for identification of outbreaks, use in individual transmission events, and in the longer term, of course, the utility of whole genome data, things like vaccines and mutational events that occur in the virus over time, but also in the use for things like therapeutics. And although therapeutics have taken something of a backstage in the media, the reality is that there are emerging therapeutics such as monoclonal antibodies, which are very efficacious and which work quite quickly. However, mutational events in the virus can be associated with loss of response to those therapeutics. It's also important to think long-term in terms of outbreaks such as this, and what we call phylogeography, the way of looking at the virus spread genetically, is supported internationally by things like NextStrain and nationally by things like AUStracker. But it really allows us to see how virus is spreading, and that's one of our aims within this project. This virus is less error-prone than other RNA viruses. It does accumulate fewer mutations, but it does get back to the fact that if we are to use vaccines and if we are to use therapies, there will be mutations in the virus, and whether they're active in preventing the virus from responding needs to be managed in real time, and certainly that's what a lot of this work is about. The other point is that the whole genome work underlies future studies and things such as looking at the whole virome, and in our case we use oligomers, Unlike Dr. Zachariah, we don't use billions, we only use millions. But even logarithmically smaller, what this allows us to do is to identify the entire virome component of an infected individual. And so when we're looking at the sorts of things that have been talked about, such as the changes in bradykinin cascades, we can also look at not only the characteristics of the virus itself using whole genome sequencing. We can look at the particular aspects of it. We can look at characterization simply with things like viral load, but we can also look at co-infecting viruses, and it's certainly in work that's been done, we do see that co-infections are associated with worse outcomes. Of course, translationally, which is what we're all interested in right at the moment and in the longer term, the use of things like local point of care testing, and there are platforms already available, like the Oxford Nanopore platform, are important in providing immediate local information about outbreaks, as well as for individuals. The other very translational problem that we now address, and in going forward, particularly in Australia, that we are seeing, is that there are a large number of individuals who are infected, but they have lower levels of virus, and therefore when we try and analyse that virus in whatever way, particularly with whole genome sequencing, we don't get an answer. And so, as I've shown here in one of the blocks, identifying mechanisms or methods for determining the whole genome sequence of load templates is very important. This, as I mentioned, is a national program, and one of the key features of what we're doing is to promulgate this to other sites. Some of you will be familiar with a recent Australian outbreak in South Australia. That's one of the smaller populations. The most cases so far of infection have occurred on the East Coast, but it's very important that these sites have access, and so things like multi-institutional agreements, local resourcing, and resourcing of remote areas, particularly highly remote areas in Central Australia, means that we have to have platforms that allow that to be done. Now, that involves both the availability of access to facilities. So, for example, we've talked about supercomputers, and we've talked about the utility of access. Often that's very difficult. It's often a very practical problem. And so in Australia, one of the very successful aspects of the response to the pandemic has been the low numbers, in fact, zero numbers in Aboriginal remote sites. The availability of resources such as this to anticipate the risk of that, and the availability potentially of local facilities, means that individual transmission events as well as transmission events between populations within the country can be assessed easily, and whole genome sequencing increasingly is going to be the method for identifying that. In going forward, as I mentioned, there's a number of research questions around this, there's a number of translational questions around this, and at the moment all of those are being explored through this work, as well as other nationally funded work. Thank you.
Professor Rawlinson will now be taking a few questions from the audience, and I have one here for both of you. Whether the question is, would the medium of future innovation be digital technology, or would something else replace it? And considering the future of health, which is our topic today, do you think that the future will be shaped through digital, or is there something else?
I would let Dr. Rawlinson, you want to go first? Yeah. I'll be happy to follow up.
Oh, okay. So in short, I think that where we're operating in whole genomes and where we're operating diagnostically is within the digital space, moving around of individual molecules, the use, for example, in the Illumina platform of electronic movement of oligomers, so that we can shift in much smaller amounts. The problem pragmatically that is translating that into a live person, because people are always more complex than digital answers. And so things like the virome answers and things like the dissection of individual responses that Dr. Zachariah talked about, for example, cytokine responses, which may allow exact reduction in the inflammation. For example, there's a recent paper on JAK-STAT inhibitors which are associated with a better outcome. So I guess dissecting things down to an individual level, the JAK-STAT pathway, and intervening, and then looking at that at a sort of multicellular or organismal level is important. So digital is great, but in terms of translating that into the multi-organed human being, it becomes more complex, and I think we need to look at multiple readouts. Thanks.
Yeah, so I think, you know, I certainly would bring the perspective. I mean, I certainly agree with everything that Dr. Rawlinson said, but I would also say that, you know, the opportunity space in the intersection of, you know, human biology and the digital space is really exciting to me. And I think we're beginning to see glimpses of what is out of the possible. So when I look at my early parts of my career, when back in 1995, the fastest computers in the world at the time was at Oak Ridge in Sandia, which is an Intel Paragon. Just to put that in perspective, you know, those the computers at Oak Ridge were used to, you know, sequence chromosome 5, 16, and 19, right? I mean, those are things that at that time we thought was nearly impossible. There was a lot of people who were very skeptical about the use of advanced computing for sequencing type of activity. So in some sense, as we learn more, we understand more, and then we begin to apply that more. But the reason why it's exciting is that the fastest computer in the world just 20 plus years ago, which costs a couple of $100 million and a big national laboratory to operate, today, if you have an iPhone 6 or better, you have one of those computers in your pocket. And there are 2 billion such units around the world. So what I see as Summit and the next generation of computers that will come in next year as exascale systems is allowing us to begin to imagine the future of digital technology and human biology, and begin to drive those kinds of innovations to where it becomes much more commonplace and usable by individual patients.
Well, listening to you both, you were talking about the sophisticated nature of the virus, the local mutations, but also how it is necessary. And Dr. Zachariah, you were speaking about this, the scale of coalitions, bringing universities, national laboratories, a number of stakeholders, also the industry, and producing, retrieving, mining a wide array of data. So the scale of both the infrastructure and the data has been key to the breakthroughs that have happened throughout the globe. And so my question to you both is whether you see that this development will create a gap between the more developed nations and nations with more fragile research infrastructures, or whether we can create or restructure the quality of those coalitions to engage and allow those less equipped nations to be also part of the conversation and not only be recipients, but also actors in the development process.
So I think the major scientific use of facilities, including advanced computing facilities that the national laboratories host, we truly host them for the benefit of the best science and the best ideas. And we have a peer-reviewed proposal process that makes these resources available to the best ideas wherever they might come from. And frankly, I think that as Dr. Rollins mentioned, some of these challenges and issues are geography and society specific, and engaging those questions and those challenges with these facilities would be an important thing to do, and we strive to achieve that connection because it's very important for science to advance.
Thank you very much. Final last words, Professor Rawlinson.
Very quick example. Dr. Zachariah mentioned the $200 million iPhone in my pocket. That's now a diagnostic, which is the equivalent about of a $500,000 machine in my laboratory, because we now have point-of-care testing, which all the money has brought to SARS-CoV-2 diagnosis, and that's in your pocket now. And I think that that's what's going forward, and I hope the latter of your comments, that'll be shared and democratized.
Well, thank you very much for these fantastic presentations and two important messages. We need the nature and the quality of the coalitions, and also the need to prepare long-term, as Professor Rawlinson was saying. We prepare now for the pandemic of the future. Thank you very much.
Thanks very much.